So skewness now.
Sorry, what's skewness?
The name of the lesson, which I'm about to teach you. Hey, Marana, come on. Focus now. So, in the last class, we saw how to draw histograms. And if you've done some examples in chemistry and biology, you might notice that histograms, they tend to be usually this type of shape. There's not much data for small values, and then all of a sudden you get lots of data near certain values, and then it decreases again. So like for example, for heights, you might get a lot of people that are around about, say, 165. But then as you move away from this, you get less and less people that will be that height. So usually your histogram is symmetric, like a mirror, the same on both sides. Okay? But sometimes it can be leaning towards one side. So before I go ahead, in biology, what type of shape histograms were you getting? Were they mostly symmetric?
We didn't do histogram, we just did line.
Column is in the teacher's room.
We did, for example. We didn't do histogram.
You never. Hang on. It's just answer the following question: yes or no.
Yes.
And think. You don't know what I'm going to ask you. And think carefully. Wait. Think carefully before you answer. In biology class, do it, see it, whatever. Has a picture of a histogram ever been put into your front of your face in biology class? So Colin, have you ever shown these guys histograms before?
Yes.
I think so, yeah. Was there a thing with Texas and pollen?
It was no. You did that states in a little Steven, we're right at the end.
Inconclusive.
Yeah. It's in the first hunting lecture. I mentioned histograms of 100 men and height and stuff like that.
Well, you need to.
Okay, the pollen.
But it's a good thing we're doing histograms now. Have you seen your students? No. Yeah. Your peeps, you know. All right. Okay. So then, in that case, the answer is possibly yes, possibly no. So most of the time, possibly yes. So most of the time, your data will be symmetric. Some will be bigger than the average. Some will be smaller than the average. But in some examples, it won't be like this. In some examples, it'll be lean in one direction or lean in another direction. Right. So come on. Right. So for example, here. So income is a good example. If you were to put people's income on a histogram, you would find, most people would be around about an average. Oops. But lots of people would have little money, okay? But then only a few people would have lots of money. It's hard. Let me try and draw this again. So lots of people would have a little bit of money, but then only a few people would have lots of money. So it's hard to see here, but if I draw the center here, it's not symmetric. You got much more on the left than you do on the right. Because you know this, like there'll be lots of people with no money or little money, but there'll only be a few people with lots of money. So it's not symmetric. Okay? Can we think of any other example whereby it wouldn't be symmetric, where the values that are more than the average would be different than the values that were less than the average?
Height.
Yeah, well, try and give me height is pretty symmetric. Yeah, the number of people that are above the average will be about the same as the number of people below the average. Anything else?
Stocks.
IQ symmetric? No. See, there's not too much. Usually, you're talking about money is when it's not balanced. But most things in biology would be balanced. So, like, if you're talking about heights, if you're talking about weights, these are all things that are pretty symmetric. But once you start talking about money, or sales, or stocks, or shares, or whatever, it's no longer symmetric. They'll tend to be leaning to one side or leaning to another side. So, yeah, but what I mean is, if you were to take the average height in this room, let's say it's 1.6 meters, for example, and how many people have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 people. So how many people would you expect to be above the average 1.6, and how many would you expect to be below the average? Yeah. Well, if I was to look at this room, I would say there's probably more people below the average than above the average. Would you say? Yeah, I think so, yeah. So when I say symmetric, what I really mean is, are the number of people above the average equal to the number of people below the average? Is it balanced? In this example here, because the class is quite small, no. But if you've got more people to come into the room, then I think it will start to balance out then. You don't think so?
Not necessarily. People are different.
Yeah, people are different, but when you put them all together in larger and larger groups, your histogram starts to look more and more symmetric. Yeah. If you talk about things like, even things like average heartbeats or stuff like this, most things in biology is nice and symmetric. What are you doing in biology at the moment? Is it still DNA? Okay, so you've done beats per minute and all this, and resting beats per minute and stuff like this? Okay. So if I was to put a graph of how many people have a resting heartbeat of 100 to 110 per minute, or 110 to 120, it'll all be pretty symmetric. So skewness is a way to describe the data when it's not symmetric. So if the data looks like this, when you draw your histogram, so I'm drawing a curve, but you know it should be like bars, right? So if your graph looks like this, where is most of the data? Is it above the average or is it below the average here? Above the average. So like if this was income or whatever it is, you can see there's going to be more above the average than below the average here. So we say that this data has a positive, we say its skewness is positive because in other words, there's a big tail, there's a big collection of people on the right. So there's more people over the average than under the average. And then likewise,
how is it that there's more people on the right than the left? So
I'll give you an example with some numbers then. This one here, oops. This one here would be a negative one. Skewness less than 0. So I'll give you an example if we talk about income. So calculate the average here. 10,000 per year, 20,000 per year, let's say 30,000 per year, and then 100,000 per year. So what's the average here going to be? It will be 30, 40, 50, 60, 160, 80, 40,000 is the average. So the average here is 40,000. How many people here earn less than 40,000? 3. And how many people earn more than 40,000? 1. So you can see here that there's more people under the average than above the average. So would this have a positive or a negative skew? Negative skew. That the data is leaning to the left more than it is leaning to the right. So now you have 3 descriptors. Our first one is the average. And what does the average tell us? That's like where the center is, right? Then what's our next description we have? So we have the average, and then what's after the average? What did we do after that? Huh? No? Standard deviation, remember? What does standard deviation tell us? Yeah, how wide the data is. So the average is like the center. Then the standard deviation, that's like how wide the data is, standard deviation. And then the skewness tells us if it's leaning to the left or if it's leaning to the right. So like if I draw that again, sorry. Here the average is 40,000. Now roughly what would the standard deviation be? So just roughly, how far away is the first one from the average? 30,000, yeah? How far away is the second one? 20. And how far? 10. And then how far is this way? 60. So let's just say that roughly about 20,000 is the standard deviation. So how wide is this data? Plus 20,000 to minus 20,000. But then the skewness tells us if we should go leaning to the left or leaning to the right. So was the skewness positive or negative? It was negative here. So that means when I draw my 20,000 to the left and then 20,000 to the right, I should have it more on the left than on the right in the number line. You know, it's a bit hard to explain, but I try to picture it like in space here. So if this is the average here, we know that that's the average there. The standard deviation is how wide it is. But the skewness then tells us if we should shift it a little bit to the left or if we should shift it a bit to the right. Okay? So like if I tell you the average here is 40,000 and then the standard deviation is 20,000, that makes you think most people are 40,000 and some people are above 20, an extra 20, and some people could maybe be minus 20. So that would be about 20,000 to 60,000, right? But now the negative skewness tells me I should move that a little to the left. So rather than doing 40 minus 20 and plus 20, maybe I should do 40 with minus 30 plus 10. I should move my range a bit to the left. Now we don't actually calculate skewness, and we don't, because it's a little bit too difficult to calculate. But you just need to have the vocabulary to describe it. So in the exam, they might have, after they ask you to draw the histogram, they might say then for 1 mark, is this positively skewed or negatively skewed or no skewness? No skewness, what do you think that is? Symmetric, yeah. So we have positive, negative, and no skewness. That's the first piece of vocabulary. And then the second piece is something called, now maybe somebody can figure out what this could mean. Bimodal? 2 modes, yes, exactly right. But what would that mean for the histogram? What, say that again? Yeah, 2 highest points. So the histogram would look something like this. So it has 2 modes. So what type of data do you think might be like this? I think you could go with a biology example here. So if I was to take this room here, I reckon there'd be 2 modes. And I reckon the mode on the left would be the most common height for the female students and the mode on the right for the male students. Yes, I think so. I think generally speaking the male students are taller than the female students.
Not all of them.
No, not all of them, you're right. Joseph will help bring the average up for the male side, don't worry.
He's sitting here, so.
Oh, he's honorary female, is it? Don't take this the wrong way, Joseph, but you are one bad-looking girl. Now, can we think of anything else from biology that might have two modes? Heart rate again, yeah. Basically anything whereby there's actually two clear different subgroups. So here, this would be height for the female students, and this one would be the height for the male students. They're making two different modes. Now, in fact, if you started to take more and more people in the class, this would still then average out to roughly one mode. But actually, if you look really carefully at the graph, it'll actually still look like two modes. Okay? So with heights, it's bimodal. Anything else? A lot of things in biology where you have two subgroups make bimodal data. Okay? I think Colin actually did have one to do with allergies as well. So you might have here allergies, and maybe it's the number of people who have allergies or something, I don't know. But what might happen is, different times of the year would have different number of allergy sufferers. So maybe it could be something like, one is for winter time, and then one will be during the summertime. And when you put both together on the same graph, it looks like it has two modes. So what would be much more appropriate then would be to separate it. Do one graph for winter time and one graph for summertime. But anyways, bimodal means two modes. And then likewise, what would one mode be, do you think? No, fair enough guess, yeah. But we say unimodal. Yeah. So we have unimodal and bimodal for one or two modes. We got that vocabulary? Okay, so then the next one now for our histogram is uniform. So what do we think shape is a uniform histogram? Yeah, the same height. So a uniform histogram would look like this. Roughly, they're all the same height. So what type of data can you imagine where each value would be as frequent as any other possibility? Yeah, maybe age of people in the class. So each age group would be maybe as frequent as any other age group. Anything else? So we're trying to think of something that the numbers in each group are going to be the same. That there are no really big values or small values. Got anything? No? What can we think of? Yeah, you got anything? Go on, Joseph, yeah?
I was asking, maybe the wavelength of radio waves.
I'm thinking, you're talking about radio waves. Most radio stations, there wouldn't be one common frequency. They all would have their own particular band, and each one would be as likely. I'll tell you one. If you want to think about this, try to think about, again, something maybe from finance or something from biology or something from science, where each group is equally likely to happen as any other group. So let's say, what else have you done in biology recently? You said you're doing heart rates, yeah? So, I don't know.
Mutation.
Yeah?
No.
Yeah, mutation of birds.
No. Huh?
Babies.
No.
What about, no? No. Let's think. Shh, stop, stop. Oh, I know. A very made up one, but a uniform one anyways. If you roll a dice, how many times do you expect the number 1 to show up? well, you expect it to show up as many times as the number 2, 3, 4, 5, and 6. But you see, these things, uniform doesn't really happen in nature, okay? When you're talking about data from nature, it'll usually be bimodal or unimodal. Uniform is very rare. And in fact, uniform data is usually an indication that the data is artificial rather than natural. Okay? Because most things in nature, they have a center and then they decrease from the center. Whereas artificial things would be like this, uniform. Well, if you like infect different age groups of mice or something, yeah. Okay. Let's see what else we've got here. Yeah. So what I'll do is I'll give you the questions and then without looking at the back, we'll try and draw them together, okay? Now, don't look at the back, you'll be surprised. So the first one, a positively skewed histogram. So that one there we got okay. Well, it looks like this. Yes? Yeah. Okay, and then next one now, negatively skewed, I already did for you. That's one that leans, looks like this. Oh, sorry, I did this. I'm drawing these very badly. Let me try again. Positively skewed is a big tail on the right. So that would be like that. There we go. And then negatively skewed would be a big tail on the left. Yep?
Yes.
What?
How is it positive? Positive is right.
Yeah. The tail, there's a big tail on the right.
Oh, so you're looking at the tail thing?
Yes, yeah. Now, maybe to make things easier, I'll keep these graphs up here. So this one here we said is positively skewed. Oh, and by the way, the letter for skewness is not S, it's this kappa symbol here, that's skewness. Yeah, it does actually. Forgot to take my kappa pills today. Yeah. Positive skewness, negative skewness. Right. Now, let's try and draw the cumulative frequency curve for each of these. So the first one, positive cumulative frequency. So what does cumulative frequency mean? That means you keep adding up the frequencies. So if you imagine now, if I start here, okay, and I start adding up the frequencies, will it get big very slowly or very quickly? It'll get big quickly because there's lots of big frequencies to add up and then you add the small ones. So the cumulative frequency graph would get big very quickly and then it would level out towards the top as you add these smaller and smaller frequencies in. I have 3 and 4 backwards in the answers on the back. Now, negative skew. So what do you think happens for the cumulative frequency curve for the negatively skewed data? Yeah, exactly. So the negative one, there's small frequencies to add, and then all of a sudden the cumulative frequency gets really big. So it's lots of small ones, and then it'll quickly rise towards the end. Yeah. Okay. Now, 5, a uniform histogram. So just a straight line. But what about the cumulative frequency curve? What would that be? What would it be? Come on, look up. Yeah. Go ahead, Hassan, what do you think? Steady line. Because if you think about it, I start off with this frequency, and then I add the same amount, and then I add the same amount again, and then I add the same amount again. So it's just steadily rising. So it will just look like a straight line like this. This one's number 5 here. This one here, that's 5. That one there is 7, is it? Yeah. This one here is 1. This one here is 2, 3, and 4. Okay. Alright, so I'm going to remove the screen in a moment, so I'll just give you a minute to write it down. For which? The cumulative frequency? Cumulative frequency means you keep adding, so it should always be rising. It only flattens out at the very end when you have no more frequencies. Okay, can I go to a new screen now? Yeah. So number 6 is the bimodal histogram. So we know how the bimodal one looks like. It has 2 modes. But how would the cumulative frequency curve look for this? And it's a bit more complicated.
Into the air.
Goes up and then so you get up there.
So if you start here, the frequencies keep adding and then they get really big and then they get small again. So you add a little bit and then all of a sudden you're adding a lot and then you start adding a little bit again. And you start adding little bits. Little. But then it gets really big again all of a sudden. So it climbs again. And then it starts to decrease frequency again. So it starts to level out. Like 2 steps. 2 steps. What number was that one now?
8.
This one is 8 here. And then this one here is 6. Now listen, something to tell you in the exam, okay? So what I've seen before in the exam, I've seen it this one or 2 times before, or maybe 2 or 3 times. Sometimes they just say, here is your histogram, and then for 1 mark at the end, is it a positive or negative skew, or is it bimodal or whatever. But sometimes for 4 marks, what they would do is they'd give you 4 graphs, like 4 histograms or 4 cumulative frequency curves, and they ask you to match them up with the name of them. So it'd be like they give you 4 of these graphs here and then 4 of the answers, and you're to match them up. So you need to be able to go from the description to the graph and backwards, from the graph to the description. Okay, and please note, I think the answer for 3 and 4, what did I say? 3 and 4 are backwards, yeah? Yeah. All right. Hey, relax. Joseph? So, if you're still alive, congratulations, the maths course has not killed you. So good for you. Yeah, you can work on your project or do whatever, but that's it for semester 2 maths. So we'll start revision after the break. Huh? That was the last worksheet, yeah. No, you don't.